Hello everyone. Today we'll be making a concentrated solution of zinc chloride. We will accomplish this by dissolving high purity zinc in hydrochloric acid. I need this for the plating bath in the Zinc Plating Masterclass series. There is extreme danger involved here. We will be dealing with large volumes of hot concentrated acid. We will also be producing corrosive and flammable gases. You must do this in a well-ventilated area or fume hood. At the minimum, wear gloves, goggles, and a mask. Do not attempt this if you're not qualified to do so. Here is everything that we will be using. Let's get started. I place the zinc ball into a 1 liter beaker. The hot plate is initially kept off. Using a 250 milliliter graduated cylinder and a disposable pipette, 250 milliliters of concentrated hydrochloric acid is measured out. I add a little bit of acid to the beaker and the reaction is instantly visible. Out of curiosity, I measure the temperature of the solution with an infrared thermometer, and it is about 17 degrees Celsius. The remaining acid is added. As you can see, the reaction really takes off. The bubbles we are seeing is not the solution boiling, it is hydrogen gas. I measure the temperature again and the solution is already at 61 degrees Celsius. What's happening here is a classic metal-acid reaction. The chloride ions from the hydrochloric acid combine with the zinc metal to form zinc chloride, which is highly soluble in water. At the same time, the acid is reduced to hydrogen gas, which you can see bubbling off the surface. The overall reaction uses 2 molecules of HCl for every 1 atom of zinc, producing ZnCl2 in solution and H2 gas. This process is exothermic, so as the reaction proceeds, you'll see temperature rising and the solution warming up. The temperature of the solution has reached 97 degrees Celsius. My goal here is to make the zinc chloride solution as concentrated as possible within a 1 liter volume. The hydrochloric acid I'm using is roughly 10 molar. So 1 liter contains about 10 moles of HCl. Because of the 2-to-1 reaction stoichiometry, the theoretical maximum amount of zinc I can dissolve is about half of that, about 5 moles. For zinc metal, that comes out to be roughly 327 grams. That's why I'm keeping track of the exact volume of acid added. It lets me calculate the theoretical limit on how much zinc could have been consumed. In practice, we rarely reach the ideal amount. As the acid is used up, the concentration drops and the reaction rate slows down significantly. Towards the end, the mixture becomes too dilute to fully dissolve the remaining zinc, so the actual yield will always fall short of the theoretical maximum. Now, we could get around this by adding a large excess of HCl, but then the resulting solution will be acidic, and that is a problem for the application we plan to use the solution for. In our case, we have an excess of zinc. The initial mass of the zinc ball was 423.73 grams. That is 6.48 moles, which means we would need over 1.3 liters of acid to fully react with. After a while, the reaction slows down quite a bit. The temperature has dropped to 48 degrees Celsius, so I decided to add more acid. I added an additional 300 milliliters of acid. You can instantly see the reaction pick up again. It was getting late and I wanted the reaction to run overnight. I wanted to add as much acid as possible without the reaction getting out of hand. So I decided to add some water to dilute the solution prior to the last addition of acid. Looking back, this was unnecessary. I just slowed the reaction down unnecessarily. Then I added the final 110 milliliters of acid. I ended up letting the reaction go for 2 days. The reaction is still going, evident from the gas evolution, but it is really slow. So, I decided to remove the zinc. Using a glass stir rod, I hold the zinc ball in place as I pour the solution into a plastic beaker. I'm using plastic in case the zinc ball rolls out, which would break a glass beaker. I rinse the reaction vessel and zinc ball to get any remaining zinc chloride. As you can see, the solution is quite dirty. There are contaminants in the solution. I'm not sure what they are, but at least they appear to be insoluble solids, which can be filtered out. This strange hole developed on it. I'm not sure why. It may have been an air pocket. Here is a size comparison with a new zinc ball. I want to weigh the zinc ball to see how much zinc was consumed. The zinc is dried with a hot air gun and it is weighed. The mass is now 257.39 grams. The initial mass was 423.73 grams. That means that the reaction consumed 166.34 grams, and that is 2.54 moles. We added 0.66 liters of acid. That is a total of 6.6 moles. Based on the initial acid concentration, the theoretical max zinc consumption is 215.75 grams. We are very far off from the target, which is concerning. We likely have lots of free acid remaining. I set up a vacuum filter funnel and filter out the solution. You can see all the contaminants on the filter paper. I am glad that the contaminants were easy to remove and we are left with a nice clear solution. Since we likely have lots of acid remaining, I decided to see if we can react more of the zinc and boil off any unreacted acid. I set up the same beaker on a hot plate and pour our filtered solution in. This time I turn on the hot plate. I put in a thermometer in the solution to keep an eye on the temperature. Temperature has a huge effect on the reaction rate. The common rule of thumb is the reaction rate doubles for every 10 degrees Celsius increase in temperature. My goal is to heat it up as much as possible without losing control of the reaction. the reaction picks up significantly with heat. It may look like the solution is boiling, but it's actually not. The bubbles we are seeing is hydrogen evolution. Ideally, I would like to push it until the solution is boiling and there is no hydrogen evolution, but we will see what happens in reality. Now the solution is boiling and there is hydrogen evolution. I'm going to let this run for several hours, then let it cool off overnight. It is now the next morning. It was a little cold overnight, so I warmed up the solution again to see if the reaction would pick back up. The reaction is barely taking place. You can also see all the impurities that came out again. At this point, there is certainly some acid left, but I decided to end this. Like the first time, I hold the zinc in place with a glass stir rod and pour the solution into a plastic beaker. I rinse the reaction vessel and zinc ball thoroughly to get any remaining zinc chloride. This time, as I pour the rinsed solution, the zinc ball rolls out and hits the beaker. This is exactly why we are using a plastic beaker to pour into. I set up a vacuum filter funnel and filter the solution. For some reason, the filter paper melted this time. I'm not sure why. Maybe it is because the solution is warm. I want to weigh the zinc to see how much more we were able to react, so I dry it off with a hot air gun. I place it onto a scale and the mass is 239.65 grams, so the reaction consumed a total of 2.82 moles of zinc. We added a total of 6.6 moles of acid. Due to our 2-to-1 stoichiometry, we could have reacted a maximum of 3.3 moles of zinc. We are closer to the theoretical maximum than the first run, but we are not as close as I hoped. I'm hoping that the majority of the remaining acid was boiled off. We have made the zinc chloride solution. I'm going to set aside a sample to see if we can evaporate off the solution and obtain pure zinc chloride crystals. I am also thinking of titrating a sample to see how much HCl remains. I look forward to your comments and thank you very much for watching.